Hi, I'm Fullerton.
Alex Logan. I'm Jeff McGuire, and our paper talks about cover automata.
Our research paper and the presentation provides a background on finite automata and cover automata. We discuss two different algorithms for minimization of deterministic and non-deterministic finite cover automatas and their collective comparison to the regular DFAs and NFAs as discussed in class.
A finite automaton is represented by a set of states, a set of symbols, a transition function, a starting state, and a set of final states, and it takes an input string which it either accepts or rejects. Finite automata were first written about in the early 1940s and are used today in text parsing, vending machines, traffic lights, and hardware design. The image on the left is a simple DFA which accepts all strings that start with two A's, while the image on the right is an NFA that accepts all strings that end with two A's.
Background on cover automata. A finite automaton can be seen as having structures for two functionalities. One, finite automata check the string in a language for patterns. Two, finite automata control the length of a string. In high-level programming, implementing a function for controlling the length would be easy compared to the structure of an automaton, and it's usually done anyways. So one way to reduce the complexity of an automaton would be to leave out the structure for controlling the string's length. Suppose there is a deterministic finite automaton of a finite language. If the DFA accepts all the strings in the language along with some longer strings, the DFA is considered a cover automaton. More specifically, a deterministic finite cover automaton, or DFCA. The image on the right is a DFCA for the language listed below it. Clearly, this DFCA does not only accept the language. For example, a string of 4 A's is accepted. Since all the strings in the language have a length of 3 or less, we can check the string beforehand and reject all strings with length greater than 3. The image on the left is an image of an automaton A, which is a minimal DFA, and automaton B, which is a minimal DFCA. This image shows that not all minimum DFAs are minimal DFCAs. Cover automata minimization. To make the minimizations, a DFA is transformed into a minimal DFCA for the language. The first algorithm for minimal DFCA was presented by Campianu in 2001 and had a time complexity in big O n to the fourth. This algorithm was updated later that year and had a time complexity in big O n to the second. Later in 2001, Campianu's algorithm was improved by Pon. This algorithm uses a function that computes the gap, which is one way to compute the minimal DFCA. The big O notation is n squared, and to the right is an example where the DFA has 8 states and the DFCA of the same language has 4 states. In 2003, another improvement was made by Corner. His algorithm was inspired by the algorithm of Hopcroft, which was introduced in 1971. The part that is similar to Hopcroft's algorithm is the bounded evaluation of states. This algorithm is in big O n log n. There's another algorithm that is not shown here that was introduced in 2015 by Campianu. That algorithm uses a pooling set technique to convert an NFA into an NFCA.
Cover automata is designed to significantly reduce the time and complexity of finite languages, but that is not always the case. As we can see in the table, a language that had 1,481 states in its minimal DFA was reduced to 1,323 states using a DFCA, but when the language only had 37 states in its minimal DFA, it was reduced down to just 30. These improvements have been most useful in the field of natural language processing so far, but we are yet to discover more real-world applications for them as the research progresses.